In this video, we will learn how to use the International System of Units for measurements. Units are standard quantities used to specify measurements, like dollars, gallons, grams, pounds. You have to have a unit on your measured value to give it meaning. Measurements without units are completely meaningless and just plain confusing. So, for example, if I say my commute is 13 long, does that mean my commute is 13 miles long, 13 minutes long? What does it mean? If I say my daughter is 8 old, you can probably guess that that means 8 years old, but how would you really know if it was 8 months old or 8 weeks old? You need to have units on those measured values. The International System of Units is what the metric system is based on, and that's used all across the world. Really, there's only the United States, Liberia, and Myanmar, also known as Burma. Those are the only countries that do not use the metric system as their standard unit system. And so I'm really sorry that you had to grow up in the United States. If you didn't grow up in the United States, good for you because you're going to have a leg up for these SI units. If you did grow up in the United States, well, you should just get on board with switching to the metric system so that it will make science classes easier for the rest of students forever. The United States does have a lot of SI units present. They're just secondary. So if you go to the grocery store, you're probably familiar with buying soda in 2-liter bottles. But if you do buy a gallon of milk, it will specify how many liters that is on the label. It's just not the primary unit. And so forth. All the nutrition facts, they list grams, and that's metric, but they also list calories, which are not metric. So we do have a mixture of SI units and imperial English units on all labels everywhere. The SI base units are as follows. We have the kilogram, which is a quantity of mass. We have meters for length, seconds for time, Kelvin for temperatures, moles for amount of substance, amperes for electric current, and candelas for luminosity intensity. We will primarily be using these first 5 SI units for everything, so become familiar with these very quickly. All other units are based on these units. So, for instance, liters is not on here, but liters is based on the meter. So, if you are familiar with these units, you can derive all other units in existence. You might notice that the kilogram has this word kilo in front of it. It's the only SI base unit that has one of the SI prefixes. All of these SI units can be used with or without a unit prefix. These unit prefixes are letters that stand for a scientific notation exponent. And so in this table, you have what the different units are and what they mean. And so if you're shopping for a new phone or a new camera, you might be familiar with megapixel as a unit, or a gigabyte as a unit, or a terabyte as a unit. And so these are the SI unit prefixes that tell you what those prefixes mean. So terabyte, gigabyte, and megabyte are the T, G, and M here. You might also make files on your computer and know how many kilobytes those files are. So these first ones are very familiar when shopping for computers or cameras or whatever. And then these other ones are more familiar for small things like nano. You might have heard of nanoparticles. And then centi and milli are like centimeters, milliliters. and those are on lots of different packaging and whatnot. So some of these prefixes you've probably heard before. You're responsible for memorizing the ones that are bolded: kilo, centi, milli, micro, and nano. The reason why you want to memorize these is that they will be used throughout the course, and you just have to be able to whip them out of your head really fast in order to interconvert between the base unit and the prefixed unit. And you just have to be able to do that very quickly. That way you don't have to waste time trying to look it up. Now, what some people don't realize is that all of these SI units, or any unit for that matter, people are the ones that have to decide how to define that unit and what value it represents. And so those definitions for these units have changed over time. The last major revision for what the units were defined to be happened in 2019, which is only last year. And so in 2019, definitions of 4 out of 7 of the base units changed. And so therefore your textbooks have not been updated yet. In your textbook, there's a figure for Le Grand K, the big K, which is the standard for the kilogram, until last year. And so this Grand K, they figured out that the mass of it was actually changing slightly over time. And as particle or atoms inside decayed into other elements. And so this Le Grand K was changing mass over time, and therefore it was not a good reference for what a kilogram was. And so in 2019, they just decided, you know what, let's get rid of any physical object on Earth and instead define these units by 7 constants. Constants means never changing value. And so all of these constants are what the 7 base units are based off of, such as the speed of light, Planck's constant, elementary charge, and Avogadro's number. And Boltzmann constants in there too. So you don't have to know, you do not have to know these 7 defining constants and their weird units, but these 7 constants are what our different metric units are based off of now. So some of the base units were already previously defined by those values. And so, for instance, the meter was based off the speed of light, well, the frequency of the speed of light in a vacuum. It's the length traveled by light in a vacuum in this many seconds. And so the meter is slightly longer than a yard. So if you're familiar with a yardstick, which is 3 feet long, a meter is just slightly longer. And then a centimeter is 1/100th of that. And so the metric system is great because all of these fractions are based on tens, whereas an inch is 1/36th of a yard. And so working with the English system, you have to remember some pretty unique conversions. But with the metric system, think of like century, which is 100 years. And so a centimeter is 1/100th of a meter. So all of the SI units are really easy to convert because they're all based on tens. The kilogram is our unit for mass. Weight is often associated with mass because they are very similar, especially when we're here on Earth at constant elevation. The gravitational pull on mass is weight, but the gravitational pull is pretty much constant at our elevation, and so mass and weight, like we're going to pretty much treat them very similarly in lab, but technically we are trying to record masses. And so the mass of a unit is a mass of how much matter is contained within an object. We'll primarily be working with grams or milligrams in lab rather than kilograms, but whatever. And so this is a picture of a nickel on a balance, and a nickel weighs 5 grams. Temperature is a measure of the average amount of kinetic energy the atoms or molecules have in a sample of matter. We will be working with primarily Celsius and Kelvin, and not so much Fahrenheit. Fahrenheit, though, is what weather reports in the United States are reported in. And so, you know, on a warm summer day, we are around 100 degrees or 115 degrees in Fresno. And then on a cold day, we might be around 40. So you're familiar with the Fahrenheit scale for temperatures, but in the lab, we'll be recording in Celsius. To kind of give you a reference point, in the Fahrenheit scale, water boils at 212 degrees Fahrenheit. In Celsius, that's set as 100. Celsius, they picked the freezing point of water to be 0 and the boiling point to be 100. And then they just divided it up into 100 increments. And so the Celsius scale is based off of the freezing point of water and the boiling point of water. The Kelvin scale, which is quite unique, it's set 0 to be where motion stops. And so you have to be really, really cold to get your atoms to stop moving. That's the absolute coldest temperature possible, and so it's called absolute 0. From that point, water freezes at 273 Kelvin, and it boils at 373 Kelvin. You'll notice that the difference between boiling and freezing is 100 on both the Celsius and Kelvin scale. On Fahrenheit, though, it's 180 degrees difference. And so the spacing of the increments on the Fahrenheit scale is much smaller than on the Celsius to Kelvin scale. Time is recorded in seconds, and then I have the official definition of a second down here. It's based off of the radiation of a cesium-133 atom, and that's kind of a nice trivia fact. Volume is a very important thing that we will be reporting a lot in lab, but it's not one of the SI base units. And so a liter is not one of the SI base units because it's based on length measurements. So volume is, for instance, the volume of a sphere is 4/3 pi r cubed. And so you would record the radius length and then follow this equation to find the volume of a sphere. Similarly, to find a volume of a cylinder, you find the area of the circle, which is pi r squared, and then you multiply it by the height. To find the volume of a rectangular prism object, you multiply the length times the width times the height. To give you kind of a perspective of size, 1 decimeter cubed is equal to 1 liter, and so we are going to be primarily working with much smaller increments, and so I recommend memorizing this conversion, which is 1 cubic centimeter is equal to 1 milliliter. That, I think, is the easiest one to memorize, and so I recommend memorizing that conversion. If you've already memorized that conversion, you can also memorize this 1 decimeter cubed is equal to 1 liter if you want to.